Welcome class to our video notes section on 3.3, where we are looking at how to find where a function is increasing and decreasing, and using the first derivative test to combine with that information of increasing and decreasing to locate maximum and minimum values. So it's related back to section 3.1. Now, just a really quick review on what it means for a function to increase is the y values are getting bigger. So right here it's saying f of x2 is bigger than f of x1, and x2 is bigger than x1. So basically y gets bigger as x gets bigger. And then in a decreasing function, notice the x's are still getting bigger. It's the same x relationship. So x2 is more than x1, but f of x2 is less than f of x1. So this is y is getting smaller as x gets bigger. So down here are some visuals to kind of help us see that. So these first two are functions that are strictly increasing. So if I were to pick like an x1, say right here, then the y value would be f of x1 would be right around there. And then if I go to the right, because x2 is more than x1, put my x2 over here, so the f of x2 would be up there. I can see that it's higher than f of x1. So basically the y values were going up as x went to the right. Same here. So let's say I pick like x1 like right there. So my f of x1 is down here. And then if I move to the right on the x-axis, say over here, there's my f of x2 is up here. Again, I can see my f of x values went higher as x went to the right. So when this says x1 is less than x2, it basically means x is moving to the right. Now, this picture and that picture are when f is decreasing. So it's the same idea for x. So I pick an x1 over here, and then I'd have an f of x1 up a little bit higher up on the y-axis. If I slide to the right on the x-axis to get x2, because x1 is less than x2, so x2 is further to the right, that y value is lower. F of x2 is lower than f of x1 was, meaning the y values are going down as x goes to the right. That's what it means to decrease. Same thing happened here. So let's say I pick x1 somewhere close to 0. There's my f of x1. And then I go to the right, because x2 is more than x1. Pick that point right there. I can see again my f of x2 is lower than my f of x1, meaning my y values were going down as x went to the right. So in both scenarios, increasing and decreasing, the x values are getting bigger. And so this increasing is not referring to x, it's referring to the y values. This means that the y values also get bigger as x gets bigger. Whereas if it's decreasing, again, that's referring to the y values because x always is getting bigger. It's always moving to the right. But if the function is decreasing, that means the y values were getting smaller as x got bigger, meaning they were going down. This picture here is just showing like something where the function has a combination of the two. So it's neither increasing nor decreasing because it does both at different intervals. So you can kind of see it was increasing, then it decreased for a little while, and then it began to increase again, and then decrease again. But then I also want you to notice that where it changed from increasing to decreasing is a turning point. It's an extreme value, right? This was a max. When it changed here from decreasing to increasing was at a min. And then there was a little bitty max right there when it changed from increasing to that little short interval of decreasing. So locating where a function increases and decreases, and specifically where it changes from one to the other, can help us find max and min values on the graph. So that's kind of the connection between the two. So let's look at our steps, or actually just some facts about increasing and decreasing functions. If your derivative is positive, then your original function will be increasing because the derivative is the slope of f, right? We have to always remember that. So if your slope is a positive slope, we know what positive slopes look like. They go that way. They go up as x goes to the right. So then if your slope is going up, then your graph of f must be going up also. For when your slope is negative, then your function is decreasing, going down, because if you have a negative slope, right, if your derivative is negative, that means it's a negative slope. That would look something like that. Then and that's tangent, right? That's tangent to the function f. The function f must also be going down, must be decreasing. Now, where your derivative is 0, must be changing from increasing to decreasing. It's either constant or it's changing direction. Because in order for a derivative to pass from positive to negative, it'll have to cross through 0. So those zeros of the derivative can help us locate where a function might be changing direction. But let's just focus on the increasing, decreasing part at first. So to determine where a function is increasing versus decreasing, you first find the derivative. You find the derivative, you set it equal to 0 to locate these places where the derivative is possibly changing sign. And then you make a sign chart where you break your domain over those critical numbers. You'll see what I mean by that in a minute. Then that'll basically give you a bunch of intervals, right? So your intervals are based on your critical numbers because you break the domain up over those critical numbers. It forms intervals. You check the sign of your derivative at each interval. That'll help you know the direction, right? Positive derivative means increasing function. Negative derivative means decreasing function. If f prime is positive, f is increasing. If f prime is negative, f is decreasing. And that's pretty much how we locate the intervals. Just look for the sign of f prime. So let's go ahead and try that with example 1. I'm going to start by finding the critical numbers of f. Those are values where f prime is either 0 or undefined. Of course, this function is a polynomial, so it's defined everywhere. And its domain is all real numbers. There's no value of x that makes it undefined. So this is going to go all the way from negative infinity to infinity. But let's go ahead and find the derivative and find where it's equal to 0. So I'm going to use the power rule for this derivative. So I have 3x squared. And then when I multiply 2 to 3/2, the denominator will cancel. And then I just subtract 1 from the power. So I get 3x squared minus 3x. I'm going to set that equal to 0. I'm going to solve by factoring. So I'll just take a 3x out of each term. So I have these two factors, 3x and x minus 1. So I get two critical numbers, 0 and 1. So these are values of x that make the derivative 0. So they possibly could be places where the derivative is changing sign. So what I'm going to do is I'm going to start from negative infinity, right, the left part of my domain, but I'm going to go up to 0, my first critical number. Then I'm going to take the interval in between each critical number, and then I take the rest of the number line. So it's kind of like you're picturing your number line. You're picturing this domain as the entire number line, but at 0 something special happens, and at 1 something special happens, and so it splits it up into 3 sections, if you will, of the number line. So what we want to know is whether or not f prime is positive or negative in each of these sections. So we kind of think about some x values in here. So maybe I can use -1 for the interval to the left of 0. And I just want to check, is my derivative positive or negative at -1? I like using the factored version, by the way. Doesn't matter which version, but sometimes that makes it really easy to determine the sign. So I can see that this would be -3. I can see that that would be -2. And a negative times a negative makes a positive. So my derivative is positive. What does that mean? That means my slope of f is positive. That means f is increasing. It's going up. It has a positive slope. Okay, then between 0 and 1, so maybe like 1/2 would be somewhere in between. I can check that with, again, I like the factored version of my derivative. So here I have 3 over 2. Here I have negative 1/2. A positive times a negative makes a negative, so I have a negative slope. My function f is decreasing. Then for the last interval, maybe I'll pick 10, right? 10 would be somewhere to the right of 1. I like using 10s. They're just easy to multiply by. So this would be 30, and that would be 9. That's going to give me a positive number. So my slope is positive. My function is increasing. So this helps me determine my intervals. But notice, it also helps me spot, oh, there must be a max over here, right? Because the function went up and then down. So it must hit a max. And then, hey, there must be a min right here because the function went down. Okay, why am I not able to draw that straight? And then up. So I know I'm going to have a max at 0 and a min at 1, but that's coming later. Right now we're just figuring out increasing and decreasing. But look, this is the actual graph from the graphing calculator, and it does do that. It goes up until 0, and then down until 1, and then up. So those really were where the maxes and mins were. So to answer the question, because it just wanted to know the intervals, so for increasing, there were actually 2. There was the interval from negative infinity to 0, right? My derivative was positive there, so my function's increasing. Union, this is the symbol we use, by the way, when we want to combine. I want to combine this interval together with that one. I use my little union sign. 1, comma, infinity. That was the other interval where the derivative was positive, meaning f is increasing. And then for decreasing would be that middle interval from 0 to 1. So then that's our answer right there. So try this one. See if you can get the intervals for increasing and decreasing. Okay, so here's the answer down here. Hopefully you got that this function of sine x minus 1, which is pictured here, that's the graph of sine x minus 1 from 0 to 2 pi, is increasing from 0 to pi over 2 and also from 3 pi over 2 to 2 pi. So that was this part and that part. And then it's decreasing in between from pi over 2 to 3 pi over 2. So basically what you do is take the derivative of sine x minus 1, which is cosine x minus 0, and set it equal to 0. And whenever we're solving trig equations, we kind of go back to the unit circle. So cosine is 0. Cosine of an angle on the unit circle is the x-coordinate of the ordered pair where that angle would kind of hit the unit circle. So that is 0 at pi over 2 and 3 pi over 2. So that means cosine x is 0 at pi over 2 and 3 pi over 2. So those are my critical points. So I took this domain of 0 to 2 pi and split it up over pi over 2 and 3 pi over 2. So 0 to pi over 2, that's quadrant 1 on the unit circle. Cosine is positive in quadrant 1. So you can evaluate it. You could maybe pick, say, pi over 4, and that's rad 2 over 2, which is positive. Or you can just know that cosine's positive between 0 and pi over 2 from the unit circle. Pi over 2 to 3 pi over 2, that's quadrants 2 and 3. And cosine is negative in both of those quadrants. So my derivative, which is cosine, is negative in this interval. Or you could pick a value like cosine of pi is negative 1, and that would show you as well. And then from 3 pi over 2 to 2 pi, that's quadrant 4. Cosine is positive in quadrant 4, but you could maybe pick an angle in quadrant 4 like 5 pi over 3. Cosine is just 1/2, positive 1/2 there, so it's positive. But the main point of that is to figure out the direction. So if the derivative is positive, the function goes up. If the derivative is negative, the function goes down, and you can kind of see that in this graph down here. It went up, and then down, and then up. So that's the answer for the U-try. So now we're going to do a few examples that use the first derivative test. The first derivative test combines the finding of critical numbers along with the sign of the derivative to the left and right of the critical number. If you put those two things together, you can decide without having to plug values into the function whether or not they are minimum versus maximum values. In section 3.1, we found the critical points and then we just plugged them in to see is that a max or a min. But we needed the graph to know because sometimes you can't tell without the graph. But with the first derivative test, you can tell. This is how you tell. So first of all, you check to make sure your derivative changes sign. So that's important. The derivative has to change signs at your critical point, at x equals c. So remember, we're talking about c is a critical point. That's a value that makes your derivative either equals 0 or maybe makes it not exist. So that locates a critical point, but a critical point is not necessarily a max or a min. The derivative has to change signs specifically. So if a derivative changes from negative to positive, then we know at that point f has a minimum. So negative to positive gives a minimum. If f prime changes from positive to negative, f will have a maximum. If f prime does not change signs, f does not have either a minimum, maximum, or a minimum. Let's look at some pictures. So this first picture here is where, here's C, here's our critical point, right? At C, I have a horizontal tangent line, so f prime of C is 0. To the left of to the left of C, f prime is negative, and then to the right of C, f prime is positive, creating a minimum. Because if you have a negative slope, your function's decreasing. If you have a positive slope, it's increasing. When you change from decreasing to increasing, you hit a low point, a minimum. So that's this. Negative to positive derivative means minimum on the original function. And then vice versa, if you go from a positive slope to a negative slope, you go from increasing to decreasing, you're going to hit a max. Again, that's at my critical point of C. That's where my derivative was 0. To the left of it, the derivative was positive. To the right, the derivative was negative. So it went from positive to negative, created a maximum. But there is this scenario, we saw this in the 3.1 video, that you could hit a critical point. Your derivative could be 0, right? So C is a critical point because my tangent line there is horizontal. I have a 0 slope. But the sign of f prime did not change around C. To the left of C, it was positive. To the right of C, still positive. What does that mean? That means f was increasing, but then it flattened out for a minute. Okay, maybe it was at rest for a second. And then it began to increase. It never actually turned around and went down. It just kept going up. So this is no change in sign for f prime, which resulted in no change in direction for f. It flattened out, hit a 0, but it didn't change sign, continued being positive, which means f never decreased, it continued increasing. Same thing's happening here. Here's C, right? F prime of C is 0. Function did flatten out, but it never changed sign. It never turned around and went up again. It just had a negative slope, meaning it was decreasing. 0 slope, meaning it flattened out, and then negative slope again, meaning continued to decrease. No change in direction means no max or min. Instead, we call that an inflection point, not a turning point. So, moral of that story is you look for a change in sign from negative to positive or positive to negative to locate max or min. Let's try an example 2. So example 2 wants us to identify the open intervals where f is increasing or decreasing. So we're going to do that, but we're also going to find the maximum and minimum values for f. So first notice that again it's a polynomial. So that means it's defined everywhere. So that means the domain for this function is all real numbers. So we're looking at this interval from negative infinity to infinity. So let's go ahead and find the critical numbers of f. That's where f prime of x is equal to 0 or does not exist, although f prime will exist for all these. So f prime is equal to 2x plus 6, just using the power rule and constant multiple rule. And the derivative of a constant is 0. I take my derivative, I set it equal to 0, and I solve for x. This is how we locate our critical points. So x is negative 3. That's my critical point. I only have 1. So I take my interval, my domain, from negative infinity to infinity, and I just break it up at negative 3. So just basically cutting the number line in half into 2 parts. And then I just check the sign of f prime on that interval. So remember f prime is 2x plus 6. So to the left of negative 3, maybe I'll use negative 10. So negative 20 plus 6, that's a negative, right? So my function is decreasing. And then to the right of negative 3, maybe I'll pick 0, because that's to the right of negative 3. So I'd have 2 times 0 plus 6, which is 6, which is positive. So the function increases to the right of negative 3. So I can see just visually that it must hit a minimum value at negative 3. You can look at the graph as well. I can see, okay, yeah, it was decreasing. Here's negative 3 and then increasing. So that is a minimum value. In fact, we can even tell that it's an absolute min. In fact, we wouldn't even need the graph to know that because it never turns around again. There's only these two intervals. There's only one time where the derivative changed sign, and that was at negative 3. So I know that on the left side, it's basically just going down the whole time, which means if you go left, these values are always higher over here. And then I know from negative 3 to infinity, the derivative will stay positive that whole time, meaning f will increase that whole time. So this point that it hit when x was negative 3 is the lowest point on the graph. So I can see that this function has an absolute minimum at x equals negative 3. Now, to find what the minimum is, I'd have to plug it into the equation. So the minimum is equal to f of negative 3, which is 9 minus 18 plus 10, which is negative 9 plus 10, which is 1. So I can see right there that point is at negative 3, 1. So the lowest value this function hits is 1. That's the minimum value, and then it happens at x equals negative 3. Now for the interval part of the question, we can say that the function is increasing from negative 3 to infinity. You can see on the graph, that's where it goes up. And then it's decreasing from negative infinity to negative 3 for this interval here. Why don't you guys go ahead and try this one? Pause your video and see if you're able to get the correct intervals and the correct max or min value for f. So for this one, you should find that it has an absolute minimum at 0. And that's because 0 was the critical point. It was the one place that made the derivative equal to 0. By the way, our derivative turned into a fraction, but the numerator could not be 0. So in this case, our critical points are just values that made the derivative not exist, right? So f prime of 0 does not exist. So that's the other type of critical point. And the domain for this function is all real numbers. So we're splitting up this interval, negative infinity to infinity, over 0. So we have the part to the left of 0, the part to the right of 0. On the left of 0, the derivative was negative, which means the function decreases. On the right of 0, the derivative was positive, which means the function increases. So it looked kind of like this. It was going down and then up. And so I can see from just the chart that there's a minimum value at 0. So we can locate that. And then to find the minimum value, I had to plug it in. So the equation was x to the 2/3 minus 4. So 0 to the 2/3 is 0, and then minus 4 is negative 4. So that's how we get the actual value of the minimum. Then for the increasing and decreasing intervals, it was increasing here from 0 to infinity, and then it was decreasing from negative infinity to 0. For our last example, we're going to look at this function 1/2 x minus sine x. We're going to locate where it's increasing or decreasing, and then also locate its max and mins over this open interval from 0 to 2 pi. So first we find the critical numbers. That'll be where f prime of x is 0. So first I'm going to find f prime of x. So derivative of 1/2 x is 1/2, and then derivative of sine is cosine. So there's my derivative is 1/2 minus cosine, and then I set that equal to 0. So I would subtract the 1/2 to the other side and then divide both sides by -1. So I have to figure out when cosine of x is equal to 1/2. So it helps to remember the unit circle. So if you kind of sketch out a unit circle, I just did quadrant 1. If you remember, there's these different angles. So there's 0, there's pi over 6, which is this first one here, pi over 4, and then pi over 3 is this one just before pi over 2. Pi over 2 is that 90-degree angle. And the cosine values are the x coordinates. The 1, the rad 3 over 2, the rad 2 over 2, the 1/2, and the 0. The x coordinates at each of these points. So we need to figure out when it's positive 1/2. So that would be when cosine is positive, which is when you're in quadrant 1 and also quadrant 4, because that's where my x coordinates are, right? Cosine is x. That's where they're positive, I mean. X is positive when you're in quadrant 1 and 4. So I also have these points down here. You'll notice the y coordinates are all negative, but the x coordinates are still positive in quadrant 4. So then the angle that gets to where cosine is 1/2 in quad 4 is 5 pi over 3. So those are the solutions to this, pi over 3 and 5 pi over 3. So those are my two critical points. So I'm going to take this interval, 0 to 2 pi, but split it up over pi over 3 and 5 pi over 3. So these are my three intervals, which if you look at the unit circle is from, I'm going to color code this, so this is the first interval, 0 to pi over 3. And then this is the second interval, from pi over 3 to 5 pi over 3. So it's a long interval, right? And then the last interval, I'll keep that one open so that this is the last one here, from 5 pi over 3 to 2 pi. Well, no, maybe I'll make it pink. So those are my intervals. I'm looking at it in terms of the unit circle because it'll help me when I'm trying to figure out the sign of my f prime. Remember, f prime is 1/2 minus cosine. So if I look at an angle between 0 to pi over 3, maybe this one, or maybe pi over 6. So if I do 1/2 minus cosine of pi over 6, cosine of pi over 6 is right here. It's bigger than 1/2. It's rad 3 over 2, right? Rad 3 is bigger than 1, so rad 3 over 2 is bigger than 1/2. So if I try to subtract a bigger number, I get a negative. So 1/2 minus cosine x is negative in this first interval that I have in blue. Here, I'll color code them up here as well so you can kind of follow along where we're at. So I picked the angle, pi over 6 for this first one and got a negative value of the derivative. That means that this function, 1/2 x minus sine x, is decreasing on that first interval. In the second interval, I can pick any angle in this whole entire green area. So I'll just pick an easy one. I'll pick pi. And then I'll do 1/2 minus cosine of pi. Now see, cosine of pi is negative. It's -1. So I'm definitely going to get a positive because I'm subtracting a negative. I get 1.5. That's positive. And if I were to pick any angle in here, I would get a positive because for this little part right here, my cosine value, which are the x's, they would all be less than 1/2. And then any cosine value in quadrant 2 or 3 is negative. So if you're subtracting a negative, you're definitely going to get a positive. And then any angle in here, the cosine value would be less than 1/2 because it's the x coordinate, and those x's are all less than 1/2. So that's why anything in this whole green area will give you a positive derivative, which means the function 1/2 x minus sine x is increasing that whole time. Just a quick peek at the graph that I got on the calculator. This whole time it was increasing because the derivative stayed positive that whole space from there all the way to there. Then for the last interval, between 5 pi over 3 and 2 pi, that's this space over here, I can maybe pick like 11 pi over 6. And so 1/2 minus cosine of 11 pi over 6. Cosine of 11 pi over 6 is rad 3 over 2 again. So I'm back to the point where I'm subtracting a number bigger than 1/2, and I'm subtracting it from 1/2. That gives me a negative. So my derivative is negative, my function is decreasing. So I went from decreasing to increasing to decreasing. You can see that in from the calculator, right? Decreased, increased, and then decreased. So I hit a minimum at pi over 3, and I hit a maximum at 5 pi over 3. And so that's what the first derivative test tells me. It says I have a relative minimum at x equals pi over 3, and I have a relative maximum at x equals 5 pi over 3. I could tell that just from my sign chart. And then in terms of the increasing and decreasing intervals, so for the increasing interval, we'll say that was this one here. That was from pi over 3. That was the longest stretch. Pi over 3 to 5 pi over 3, this whole entire part of the unit circle, or this whole entire part of the graph. And then there were 2 different places where it was decreasing. So that's 0 to pi over 3. The derivative was negative there. Union 5 pi over 3 to 2 pi. Derivative was negative there. You can see that on the graph. It was decreasing and decreasing. So that is basically the gist of 3.3. That concludes our video. See you guys in class.